All right, so thanks everyone for coming. Today I want to return to what Mike and I were doing recently with the using the Williams and Stay construction, uh, in particular how it relates to the proof rules. So we still have, Mike and I are still working this out, but things are coming together nicely. So I just want to reiterate. So we went down this path of looking at the proof rules and then formulating an alternative to the Williams and Stay construction, because I was concerned that the Williams and Stay construction did not have scope for the other kinds of containers that I want to support. So in particular, I want to be able to support at least linear containers, and potentially others. And the Williams and Stay construction is really focused or amenable to set-like containers. So you can get multi-sets. You can probably get probability distributions, although we haven't actually looked at that in any detail. But I want to at a minimum get linear containers for a wide variety of reasons, and I especially also want to be able to do updatable containers. And the reason for being able to have updatable containers is that we want to be able to have the thing fit directly onto repositories like GitHub and other kinds of databases. So let me just stop there and make sure that, kind of we're all on the same page. Does this make sense? Everybody following?
Greg, when you say updatable containers, are you thinking about the Git repositories, for example?
Yes, exactly. Get repositories, databases, and go ahead.
I'm thinking that Git repository. I don't see Git repository as updatable because you are always you are only able to add new stuff.
No,
you can say that you can.
No, you can delete.
History.
You can delete things as well.
Mm-hmm.
No, like the history will show that you have removed code from a repository.
Oh, I see. You're talking about the content, not the.
Yeah, I'm talking about what the container contains. Yes.
Yeah.
Yeah.
I just have one question about the. You mentioned the list. You want to have vectors instead of lists. So I'm wondering why lists are not.
No. We want to be able to do lists as well, but lists don't have the same power object property. So there is no list of all sublists. And the reason is because all the sublists of a given list are not orderable. Mm-hmm. You can't create an order, and since you can't create an order, you don't know how to place them in a list.
And from vectors, you can do it.
So with vectors, there is a notion of a power object. Again, it's not as clean as sets, or it's going to have some properties that are surprising. I see. But so we want to be able to do all of those things, but we also want to be able to say exactly the properties of the logic that you get out of it. Does that make sense?
Yes. I think I don't have like good understanding of power object. This is something that
so it's the all subparts of a thing. Mm-hmm. So you have a thing, now you want to take all of its components and build an object of the components, right? So you know what it means to take the set of all subsets of a set.
If I have set of 1, 2, 3, I can have 1, 1, 2, 1, 3, right?
Yeah, exactly. All the subsets, and I can form a set out of all those subsets, at least for finite sets, right? Well, once you start to get to larger sets, then the set of all subsets might not be a set. It might have to be a proper class. And so it turns out that even in sets, this idea of taking, all of the parts of a thing and then assembling that into an object it doesn't always yield the kind of object that you think it does.
Okay.
Yeah. So in particular, one of the more interesting things about lists is that if you take all the sublists of a list, you have two choices. So one choice is you say, well, I can't make a list out of that. And you say, well, okay, that we're done. Can't make a list out of that. The other choice is to say, no, you've got to give me a well-ordering theorem, right? If you give me some principle that says that everything can be ordered, then I can order all the sublists of a list. So you see, there's two sides to this. One side is I can't make a power object of lists. The other side is if you give me a well-ordering principle, which is equivalent to axiom of choice, then in fact I can make a list of all sublists, because the well-ordering principle gives me an order for all the lists, and so I employ that to create the list of all the sublists. Right. So, but
when you create a list of sublists, are you talking about a list where you are concatenating all of the sublists?
It would be no, you're not concatenating them. You're actually including them as sublists in a larger list.
Okay. So basically you have a list of lists.
Yes, lists. You have a list of lists, right? Right. And some of them are not comparable.
Mm-hmm.
Right. So in particular, if I have the set A1, B2, C3, then the list that is ABC, that's a sublist, and the list that is 1, 2, 3, that's a sublist, right? I can't compare them.
Mm-hmm.
So I don't know what order to put them in.
I see.
So I can't form a list of sublists unless someone hands me a well-ordering principle. Then that well-ordering capability would allow me to put them in a particular order, and so then I can return the list of all sublists. Right. So in different set theories, in different foundations of mathematics, I will get different answers to creating the power gadget.
I see.
Right. And that's directly related to logic, the side of the logic that has to do with containers.
Interesting. Okay.
Yeah. So I mean,
thanks.
This is hard won understanding for me. Just trying to come up with notions of decomposition and reassembly has been at the heart of my investigation for several years. And that's one of the reasons why Jade Masters' new paper on decompositions has caught my attention. And it's also the reason why Lee Cronin's work on assembly theory has caught my attention, because both of them are also wrestling with this same issue, which has to do with taking things apart and reassembling them into larger structures. So I would urge everyone to take a look at Cronin and Walker's assembly theory. They have remarkable results in the sense that they can detect a form of complexity that's objective. So Cronin's assembly index has been used successfully with NASA to detect molecules that arise out of evolutionary processes versus molecules that don't. Right. So NASA is using this assembly in the techniques arising from assembly theory and the assembly index to arm their probes to look for alien life. So this is how far-reaching these ideas are.
Yeah, interesting. I was listening. I think Lex had interview.
Yeah. With he did one with Cronin, and then he also did with Cronin and Walker. Yeah. And yes, so absolutely. So all of these things are connected, and it's really important to understand how they fit together. And it's taken me a long time to understand that you get different maths, different foundations of math will give you different capabilities in your power object construction. And so,
can I just ask you?
Go ahead.
One like a little bit more, maybe side question. With different foundations, I was listening Stephen Wolfram, where he was saying he thinks that it doesn't matter what are the foundations; you will always get to the same point. No,
that's absolutely false. That's easily demonstrated to be false. So ZF
maybe not the same, but you can get to the point where you can with different foundations you can prove the same things. I think
no, that's completely false. Okay, so I mean, like in this day and age, to have a mathematician say that is completely irresponsible. So we know that set theory without axiom of choice is very different than set theory with axiom of choice. Those are two different foundations, and they give you completely different worlds. And
maybe I'm not saying correctly in this form, but he's saying from very simple pieces that you can build your foundation. And then from there, basically, you can do whatever you already have, but you can get to the foundation by in different way. Because
so look, you know, whether you start with type theory or set theory, you can get to similar universes, but or whether you start with set theory versus category theory, you can get to similar universes, but even there, things diverge so much that you see the problem differently, and it's very easy to miss details like, you know, have I actually encoded ZF or have I encoded ZFC, right? Because if you start down this process of type theory, you're more likely to be constructive, right? Whereas if you start down the process of set theory, you're evidently, historically, less likely to be constructive. So whether we take this nuanced view of his meaning, or we take the sort of simplistic view of what Wolfram is saying, neither of them are true. I'm sure that, you know, he has reasons for saying what he's saying, and if we talk to him long enough, we'd get to some common understanding. But you know, that statement, there's very few ways in which you could make that statement true. All right, let me do a screen share now. So it's been a while, so you probably don't remember these rules, but essentially these are the kinds of typing rules that we want just for the term formation, right? So you know, so as an example, if you know that some Y, where Y is some subset of all the possible channels, and P is a process that is some subtype of processes that is, you know, a subset of all the possible processes. If you're given this information, then you can conclude that the for Y from XP, so this term, which we know how to form in rho, is going to be of this type, which is itself a subset of the set of all possible processes. Does that make sense?
Yes.
Okay, and the same is true. So this is actually very powerful, right? Because this allows us to form subtypes of 4 comprehensions, right? So in particular, I can use this kind of construction to create a firewall, right? I can insist that only talking about processes where the channel that they're listening on comes from some namespace X. All right, so essentially these 2 things here, the X and the Y are namespaces, right? So I can insist that this thing is only listening on channels from a given namespace. I can also insist in this type that upon receiving something from that namespace that we only engage in certain kinds of behaviors. So for example, we could insist that we never send outside of this namespace, right? So U could be something that's like this. We're only sending on X. So so just those 2 together would create a firewall. Does that make sense?
When you say subtyping, it's like normal way of thinking of subtypes.
Yeah, but I mean, literally, by subtyping, what we're saying is subset. So U is some set of processes in some sense, and P is all of the processes you could legally build from the grammar, right? And then U is going to be a subset of P. N is all the names you could legally build from the grammar, and Y is going to be some subset of that. X is all the names you could legally build from the grammar, and N is all the names you could legally build from the grammar, and X is a subset of that. So that's what we mean.
And is this hidden, this notion of a power object when you say all the possible subsets?
Yes. So hidden inside here is some power object gadgetry. That's correct. So in particular, this thing here is a power object thing.
Oh, I see.
It shows up on the next slide as well, but in a different way. Okay. So what we want to do, we kind of have a sense of these rules. There's some other rules that we want to talk about. We kind of have a sense of these rules because they derive directly from the grammar, right? You can see how, given the grammar for Rho-lang or the row calculus, you can build these rules, right? It's completely algorithmic. There's no surprise here. It all derives from the syntax. Okay. So having said that, what we'd like to do is to interpret the rules in category theory. And the reason is because we want to be able to build these kinds of systems for a wide range of computational phenomena over a wide range of possible implementations. So, for example, I might want to implement the row calculus on a quantum device, or I might want to implement the row calculus on a chemical device, right? Or a genetic device. And so having categorical semantics for these kinds of rules allows the category theory to if you can present quantum mechanics as a categorical theory, then we can, if that theory matches the requirements for the models of these rules, then lo and behold, I get that the rules are sound for those kinds of implementations. And likewise, if you can present the chemical model of computation as a category, then I can, if that category matches the requirements for the models, then I can again line up the rules with that kind of implementation. Does that make sense?
Yes. I'm thinking we can see the memory as some kind of something that we want to use in our implementation.
Yes, that's
For example,
yeah. Go ahead.
I'm thinking that how we are addressing memory, maybe we don't want to write implementation managing some kind of arrays and the indexes in the arrays, and can we somehow translate and use memory efficiently? I'm
Yes.
thinking concretely for rolling.
Yes.
If we can go immediately to the memory, we can just increase the performance dramatically.
Absolutely, absolutely. So the thing that I'm trying to get to is a characterization that is abstract enough that we can, and yet precise enough that even though it's abstract, we can layer it on top of a wide range of potential computational substrates. And so that's the whole point of the categorical semantics. Well, I mean, there are other points as well, but the category theory is sort of right now the best way to get that level of generality. Okay, so you've seen me use these funny double brackets before. So what we're going to do is the double brackets means take the meaning of. So we're going to take the meaning of a rule like this, and we're going to supply an additional parameter. So one parameter for the double brackets or the meaning of function is the rule, and another parameter is an object in a category. In this case, we're using one, which is the terminal object in our ambient category, but it could be something else. And so what we're saying is that the meaning of this rule is a function. And the function takes an x and a p, so that's this x and this p. I didn't include y because y really is going to be treated as a variable in an abstraction, right? But if we were doing this entirely syntactically, we could include the y. And what we're going to say is, and it's also going to take a subtype X and a subtype Y and a subtype U. Oh, that should be a comma. Okay, and it's very simple. We're going to, the function is if X belongs to the interpretation of bold X given 1. So the double bracket function is a polymorphic function. It can take rules and it can take types, right? So if it is if you run the interpretation of the subtype X given 1, and which is ultimately going to give you a set, and this is going to give you, and this is you need to check if X is in that set. And likewise, you need to check if P is in the set that is generated by interpreting U given 1. So if that happens, then you want to check that this expression is in this set given 1. And you also want to check that this set is a subset of P given 1. That's the meaning of this rule. Now there's, Mike and I are discussing various ways of packaging up this meaning. But by and large, this is the meaning of this rule. And it's very straightforward, right? There's nothing really hard, right? As long as this thing gives me a set, I do, you know, element of, like there's a Scala function, right? Given this set, go and do a find and see if this lives inside that set. Same here, right? You know, I've got a process. It's a piece of abstract syntax. I'm going to go check and see if that syntax lives inside that set. And if it does, then I'm going to go and do 2 more checks. I'm going to see if this thing lives inside that set. And I'm going to see if this set is a subset of that set, right? So this basically corresponds to some Scala code, right? Now it's a little bit more complex than that, but but spiritually, morally, it's not much more complex than that. And similarly for all of the other rules. So I did two more just so you get the idea, right? So the same thing is happening for the output formation. And if you go back and you look at the previous Caspers in which we talked about the Williams and Stay construction, you'll see that, in fact, these kinds of expressions make sense, right? So if you look at the taking, the growth and decay of the sub of the representables, the Uneta embedding, then you'll see that all of these sub expressions all make sense. So all of this part just does the right thing. It's just as natural as could be. Okay. Now, the part that we were checking, the thing that is of interest is, so the Williams and Stay construction uses the Uneta embedding. And then what Mike and I have been doing to go after additional containers is to do enriched Uneta. So we have some monoidal gadget lying around, and we're going to look at this monoidal gadget. Let's call it M. We're going to look at M pre-sheaves as opposed to pre-sheaves, right? Now, how does that show up in terms of the logical rules? So we can answer that question. So these rules here, which are about or, a kind of or and a kind of and, these rules show up from the sub part of the Williams and Stay construction. So taking these equivalence classes of monics, which we talked about a few weeks ago, that's what generates and interprets these rules. And then the M part is what's going to interpret this rule. So this rule says, if you've got some judgment, so you've got some gamma, some assignment of types to the left of the turnstile, and given that assignment of types, you get that P is of type U, which is a subset of the bold P, and then some delta, again, some assignment of types to the left of the turnstile, allows you to conclude. So my friend Lucian Visick used to say, delta thinks that Q is of type V. So that's a way to read these judgments. So given these two judgments here, we can conclude that gamma together with delta think that P M with Q. So I write tensor, but it's whatever the monoidal product is from the monoidal gadget. So P M with Q is of type U M with V, and that will also be a subtype of P, or more likely it's going to be M of P, not P. And likewise here, this will be not P, but power of P. But these are the rules that come from the container. And so M is providing the monoidal part of the container, and sub is providing the sort of set, like it's providing a poset structure, a posetal structure. So just to be clear, just to remind everyone what, the Williams and Stay construction basically looks like this. Oops. Let me see. Yeah, there we go. So we take the growth and deke of the sub of the Uneta embedding, right? So that's the Williams and Stay construction. And we're modifying that in this setting to go to where there's an M here, and M is some monoidal gadget. Yeah. So that's the, sorry, just trying to line this up. Okay. There we go. Okay. So these are the, this is Williamson stay. This is a variant on Williamson stay. The sub, so the Y part is what's giving us these things here, these pre-sheaves right here. The sub part is what's giving us the and the or. And then the M part is what's giving us these things. So it appears, again, we still have tons of calculations to go through, but it appears that everything is lining up. And so now, and the reason it's important to check this is because the model checking based on this interpretation, and even worse in this interpretation, is hard to implement. But as long as we can prove that the rules are faithfully interpreted by the models, or that the rules can be thought of as syntax for the models, then we get to just do syntactic type calculations, right? So if we put all the rules together, we'll have rules like this together with rules like this, and we can just run the rules symbolically without having to check the model stuff. We don't have to go look inside the semantics. Just these are syntactic constructions, and we can so if a programmer makes a declaration like this, right, then we know how to break this up into these two things, and then we go check these two things. And if these have internal structure, say, for example, like this or like this, right, then we know how to break an assertion like this up, right? And we can just keep wandering up until we ground out in things like this, which have no additional stuff. And if you can walk from some programmer declared assertion all the way up to leaves, where you have no assumptions, then you know that the type judgment is correct. And so that can all be done syntactically, and there's an obvious algorithm for walking that kind of thing. And there are probably many more efficient ways of doing it than the obvious algorithm. So, but this is why, this is the other reason why we're doing this work. So we make sure that the rules faithfully represent the model, and then we can do the implementation just in terms of the rules. Does that make sense?
I think yes.
Okay.
So basically you're saying that the syntax described the model.
Yes. So I mean, like if you think about it, complete partial orders are, and the Scott topology are very sophisticated semantic gadgets. And you could potentially do all computation ever inside, complete partial orders with the Scott topology. But that's hard because you have to do a lot of mathematical reasoning about those kinds of gadgets. And I don't know how you would teach a computer to do that. But it turns out, luckily for us, that the lambda calculus is syntax for complete partial orders and the Scott topology. So instead of having to do all that fancy math or teaching a computer to do all that fancy math, we can teach the computer how to do lambda calculus because it's entirely symbolic. Does that make sense?
This is interesting when you say it's entirely symbolic.
Yes.
Because I was listening Cornel Elliott when he was basically discussing similar question when he said, well, everything is basically symbolic manipulation.
Sort of. I mean, I would not say that the way real numbers are represented in ARM chips today is symbolic. I would say that we gain a lot from an interpretation of addition and the other arithmetic operators in terms of the electronics, right? Which grounds out in our physical understanding of voltages. So in that sense, not everything is symbolic, but you certainly could do all of arithmetic as church numerals in the lambda calculus, but it wouldn't run as fast as something that grounds out in voltages, right?
So, for example, this analog computers that they are now using for some type of machine learning, I'm not sure.
Correct.
This part of computation, it's not easily represented as representable as some kind of symbolic thing.
That's exactly right. That's exactly right. So symbolic is kind of the so you could think of digital as halfway between symbolic and physical, right? Because zeros and ones can easily be represented symbolically, but they can also be mapped onto physical quantities. And that's why digital computing is so powerful, because it can live in both worlds.
I see. So there is no like very simple line between symbolic and non-symbolic, and we can just say this is the line, depending how what you have and how you look, right?
Or I guess what I would say is there's a crisp definition of what's symbolic, but some symbolisms have natural mappings onto physical interpretations.
Yes. I see.
Yeah. So and go ahead.
If I could just pipe in here, that this may be completely irrelevant. You'll have to decide. But some of what you're saying in terms of mapping the symbology onto physical hardware is reminiscent to me of the time that I spent in the space telescope stuff that I was doing a while back. That the representation of a real number from an optical camera in space, and then dealing with all of the mathematicians that had to do the optical math. I don't know if there's any relation between the fields, but
oh, absolutely, you're absolutely right. So when you're dealing with physical systems, they have all kinds of ways of representing physical quantities, right? I mean, like literally, if you hold a compass in your hand, right, like like the kind of thing you use to draw circles, like you can represent angles, right? And you can represent angles that are impossible to write down symbolically, right? You can easily construct things that to be transcendental. And so if you tried to write it down symbolically, you would be there forever.
yeah, I was just curious as to whether or not any of the practical research for implementation in optical cameras might be relevant to turning this into a real system.
Well, I mean, we can make OS, and what I've been arguing now for quite some time is that we can make OSLF quite handily in a symbolic way. And if we want to expand it to include languages that have transcendental entities that have transcendental characteristics in the sense of they're not easily compressible. I think that we can do that, and it's something that I've thought a lot about. Let me. So I need to go take care of some stuff before Dev stand up. But let me leave you with a thought that I think is relevant to this discussion and also connects back to what we said at the beginning in terms of Lee Cronin and assembly theory. Now it turns out that there's this tower of computation. So it doesn't stop at Turing. So you can show that there are real valued computations which are strictly more powerful than Turing. And then there are computations that are strictly more powerful than those. So you can think of, there's this tower of different computational systems where the system above the current system looks like an oracle to the current system. So for example, in the case of real valued computations, you could think of the real valued computations as oracles to the Turing machines. So you might think of that in modern terms as sources of entropy, right? So when you're writing your Java program or your Scala program and you appeal to a source of entropy, like, the temperature or, some atomic decay process or something like that, where you're going and measuring a physical quantity. That's like having an oracle that's giving you access to some transcendental or other capability. And that relationship of lower expressive power to higher expressive power extends to infinity. At every level, there's a level above it which can be an oracle to the level below. Does that make sense so far? Does the tower make sense?
Yes, I think I understand.
Okay, so this is kind of important. Now here's the interesting philosophical question. If you start with just, let's say, regular expressions, there's no way to build something inside the universe of regular expressions that is more powerful than regular expressions. You can't get there. So, and likewise, if you start with, say, context-free languages, which are more powerful than regular expressions, there's no way with context-free by itself to get from context-free to Turing complete. And there's no way to get from Turing complete to the next level up and the next level up and the next level up, etc. So wherever you draw the line, you say, okay, at, in levels up in the tower, that's where the physical world is. That's it. That's all the expressive power we've got. You can't go to the next level. So if you say, the universe is Turing complete and only Turing complete, well, we know that there are real computations that are bigger than that. It's proven that quantum machines can do things that are beyond Turing. So obviously the bar is not at Turing. Well, where is the bar?
I mean, isn't this, the essence of Gödel's theorems, that there are things that are incomputable inside of any consistent language?
No, it's more to it than that. What I'm suggesting is that is to ask yourself, where would you draw the line? Because there's no evolutionary process that's going to get you to the next level. Right? So in some sense, biology had to already be included in the computationally expressive power available at the Big Bang, because there's no process that's going to get you from regular to context-free, nothing that's going to get you from context-free to Turing, nothing that's going to get you from Turing to the next level up. Whatever phenomena you see, whatever complexity you see, it had to already have been there implicit in the computational capacity at the beginning.
This is a lot to think about.
Well, I guess we just need somebody who can have a mind big enough to know what happened at the Big Bang then.
I know. I guess what I'm trying to suggest is that maybe it is turtles all the way up. That there's no reasonable place to draw the line. How would you know if you were sitting next to an entity that could act as an oracle to your computations? How would you ever think to ask the question? It's another way of putting it is, how do you know if you're on the bus next to an alien? Unless you think to ask exactly the right question, you wouldn't know.
And in the case of context-free to Turing, you couldn't ask the question in context-free, could you?
No, you couldn't. And in fact, in general, it becomes difficult to formulate the right question. So my suggestion is maybe there is no right place to draw the line. That the universe is always willing to deliver up more computationally expressive power, but it depends upon us to be able to make, to be able to be open enough to make use of it, to make, to be available to what's already there.
And you're saying that all this is already present in the Big Bang.
Already present from the beginning, because there's no way to get, it's like if you say, okay, this is where I draw the line at computational expressiveness, then wherever you start from, you can't get out past it. There's no process that's going to get you out there.
Yeah, you need new math.
Yeah, you need something that's outside of processes like natural selection.
So this means that we can expect that in the future, definitely we will have some more computational power, which is maybe not manifested now in this universe at all.
If you accept my hypothesis, then there's always more computational power available. It's always present. It's just whether or not you have, and again, if you're a being that contains all the complexity of the universe, then it is always accessible to you, but you have to learn to be sensitive to it. Like you may not see it because you're only looking at Turing complete.
I mean, it's a similar thing Stephen Wolfram is saying, how this boundary of computational, I don't know how he calls it, where if this is your boundary as the observer, and if your computational expressiveness is if this is your boundary, basically you cannot go outside of that. Even if this exists in outside, and some observer can see you as like a lower.
Yes, that's correct. But it's even more subtle than that, right? I mean, part of what I've tried to suggest is there are lots and lots of Turing complete formalisms that still have differences in expressiveness because expressiveness is multidimensional. So in particular, compositionality is a form of expressiveness, but there are models of computation that are Turing complete that are not compositional. right? Concurrency is a form of expressiveness, but there are models of computational power that are Turing complete but don't have concurrency. There are, being able to do resource counting, so complexity is a form of expressiveness, right? Like it's really important to be able to count how much time and space is consumed in your computation. But lambda calculus suffers. It can't do that because beta reduction is so slippery when it comes to the copying of resources. So expressiveness is not like just one number, right? It's not just a single dimension. It's multiple dimensions, and each of these different dimensions has a profound impact on the shape of the computations that you write down, and as a result, the kinds of meta computations you can do on your computations. In other words, checking for correctness properties, but also checking for complexity, and also refactoring your code. So refactoring, which is something that every programmer knows is important to be able to do, sucks in Turing machines. Being able to get things done simultaneously sucks in Turing machines and lambda calculus. Works great in Petri nets, but Petri nets are terrible for refactoring. Right? Do you see the points I'm trying to make?
I have a question, and I don't want it to slip my mind. It may be off topic of what you just said. Philosophically, does this mean that completeness of expression in a stepwise manner, so we go from context-free to Turing, from Turing to something else, does this mean that as we become increasingly expressive, that the problem space that we're in necessarily becomes more complex and smaller at the same time, meaning that completeness is unachievable?
I don't quite know how to interpret all your words, but certainly completeness is only one piece of the puzzle. So completeness is, you're always going to. So one way to think about completeness is exactly as you say, Gödel, but we're relativizing Gödel. We're saying that there's always a system outside of where you are that's going to.
And my suggestion is that system outside of where you are is necessarily a smaller problem space.
Oh, no. It's much bigger.
And yet at the same time, more complex.
No. It's vastly bigger problem space.
Okay. So it's larger and more complex.
Yes. So all you have to do is to think about the naturals versus the reals.
Yeah, no, I understand the set stuff that you were bringing up before. That made sense to me. Yeah. Okay.
Cool. Well, I appreciate everyone's time and attention. I hope it wasn't too abstract, but maybe also a little bit interesting and engaging. And I will see folks in the Dev Stand-Up in 4 minutes.
Yeah,
thanks, Greg.
Super interesting. See you. Thanks.
Ciao.
Bye.